Hello students, today we are in our week 5 of our quarter 4 or our distance learning program. We are exactly in halfway. I really appreciate all your hard work in doing all the other assignments in the last 4 weeks. Today our topic is modeling with logarithms. It is about application of logarithms. If you remember last week, we learned about changing between logarithmic and exponential expressions. If you remember, we said log base b of a is c. If I have log base a of b is c, if I have that, this can be changed to a to the power of c is b. For that matter, a and b doesn't matter. You can change all these. For instance, if I say log base b of a is c, it means just b to the power of c. That is this one to the power of that should be that one. The same way, this b to the power of c should be that a. The letters doesn't matter, but the order at which we go. So this would be b to the power of c is a in this case. So today we are looking at the applications of logarithm. So I will just try to review with you some of the important formulas we need for this to do our work. First of all, exponential function, you remember it is y equals a b to the power of x, where a is the initial amount and b is the growth rate. X would be usually the time or the period at which something increases or decreases. At the same time, if you remember, we said when b is greater than 1, it's a growth, but if b is between 0 and 1, it would be a decrement or it's a decrease. So before we do the actual examples or problem solving or application of logarithms, I would like to review with you what are the important formulas we need. The first one is a equals p into 1 plus r to the power of t. This was the same thing when we were doing last week, or the other week of especially the exponential growth formula. In the week 3, especially in the week 3, we have done this when we were modeling exponential growth, where p is the initial or starting amount, a is the final, r is the percent rate of growth in decimal usually, and t is the time. So this is one of the important formulas we'll be using. The other is the decay formula. The difference is just you replace minus. Instead of plus, you use minus there, but the formula and all the variables, the quantities are the same. The variable quantities are the same. So we are applying when it is a decrement or a decay, this formula, a equals p into 1 minus r to the power of t. There is another important formula we call the natural logarithm. You remember, common logarithm is when the base is 10. Natural logarithm is logarithm to the base e, where e is a symbol for a special number called Euler's number. This is a special number like you say in geometry pi 3.14. This constant value 2.718 stands for special number where we use continuous growth when we are applying. We don't apply the previous formula. I will show what formula to be used. It has been experimentally determined this number has a close relationship to something that grows or decays continuously. So log to the base e of x, we call it lnx, natural logarithm. To mean natural logarithm, we don't write the e and the log, we just say lnx. So where do we use this number? This is when something is compounded continuously. The number e is supposed to be used. So the formula now changes for continuously compounded increase. Say a equals p e to the power of rt. So no more the previous formula of growth which we have seen here we are not using that. When something grows continuously, we are using this formula, A into PERT. P is a starting amount, the same thing like the previous formula. A the final. E is Euler's number, the 2.18, which I said it earlier in that. So this is what we are using. When we apply the application, how we go to ln would be determined, we'll see, because we are changing this equation, this exponential equation, to logarithmic, and the base would be the e. The base would be the e. So we have to, when we see the examples, it would be more clear. Okay, APERT. If it is decay, the only thing would be this RT changes to negative. Continuous decay, if your problem said that something is continuously decaying or decreasing, we use A, PE, negative RT. P, A, E, and R, and T are as above. They are the same. C is a negative there. So, some examples of this continuous growth or decay would be problems of compound interest, which is continuously growing, duplication of bacteria culture, decay of radioactive elements. These are some examples of continuous growth. So next what we do is we do one by one the examples where we apply these formulas. So after I display the question, I'll be working with actual problem solving. This is the first example. Suppose Mr. Peter saved 1,000 in a bank account that gives 6% of compound interest. Find how many years it requires for his money to quadruple if the interest is compounded annually and continuously. So we are using two different formulas here. Okay, once you see that, I'm going to do the solution. Okay. Example 1. The problem said the initial amount P is 1,000 because Mr. Peter started with that, and the rate R is 6%, which means 0.06, and it's compounded annually. We are going to find when it will be quadrupled. Quadrupled means 4 times 1,000, which is 4,000. In how many years Mr. Peter will get this? Last time, if you remember, we were creating a table and finding, but the formula we use would be A equals P into 1 plus R to the power of T. So this would be replaced by 4,000. P would be replaced by 1,000. 1 plus 0.06 to the power of T. So we are finding the time it takes so that Mr. Peter gets from 1,000 to 4,000. Okay, so this can be used directly without using table, without constructing. Now we learned last week about logarithm. So we are converting this to logarithm, but first you need to divide by 1,000. Okay, this is gone. This is also gone. What you get is 4 equals 1.06 to the power of T. Okay. Now this is exactly similar to the formula B to the power of C equal to A. So I'm changing this to logarithm if I want to get T. Log base 1.06, the base is 1.06 of 4 equals T. Already I got the time. So that's why we are learning logarithm, to find the time or how long it takes for some money to grow from original amount to final amount. Okay, so if you remember last week we learned about logarithm. To find this log, what we said was log 4 over log 1.06. This will give me the time. So what I do is log is here, I press log button, then 4 divided by, again log, by 1.06. This gives me 23.8 years. 23.8 years is required for Mr. Peter's money to grow from 1,000 to 4,000 with annual compound interest rate of 0.06 or 6%. Okay, this is question A, when it is compounded annually. Now B, compounded continuously. For this is compounded annually. We are using that formula. When it says compounded continuously, we are using the other formula which I gave you, P E to the power of RT. Okay, the formula now changes. How to do this? The procedure is the same. The final amount is 4,000. The initial amount was 1,000. E, R is 0.06 to the power of T, 0.06 T. So look, the formula is completely different from that when we are doing continuous growth. So the other procedure is the same. We are dividing by 1,000. And so I need to go back to my computer also to log in. Sometimes it goes away. Okay, anyway, so this becomes 4 equals, let me put here, 4 equals e to the power of 0.060. As you see it now, this changes to logarithm at this point. Log of base e of 4 equals 0.060. This is what we get. But if you see that we have to find what log of base e of 4 is. It is ln. If you remember, it means ln of 4, or natural logarithm, equals 0.060. ln is found below log function in the calculator. ln is here, just below the log function. So I find ln of 4, just ln of 4, which is 1.386. Let me take it as 1.39. So 1.0, sorry, it's not 1.39, 1.39. This is an approximate value. Okay, if that is equal value, but the next one will be approximate. This would be 0.060 because ln4 is more than that. We rounded it. So now to get t, you need to divide by 0.06. Divide by 0.06. So you get t would be whatever this is. So when it is continuously compounded, we divide 1.39 divided by 0.06. This will be 23.17 years, almost closer to that, 23.17 years. years, or 23 years, you can say. That one 24 if you round it. This one approximately 24 years. This one approximately 23 years when it is continuously compounded. Okay, this is the first example. So I will give the second one. The second example would be this one. Let me show it again. Okay. Few years back, an average computer costed $2,700. The cost has been decreasing with an interest rate of 5% per year. How many years is required for the average cost to be 1,000? Say, in how many years the cost decreased from 2,700 on average to 1,000? So let's do this. This would be, we are using now the decrement formula instead of the increment formula. Okay, let's do example 2. Example 2, solution. Suppose the initial amount P was 2,700. It went down, the final amount became 1,000 with the rate of 5%, which is 0.05. We are going to find how long it took for this decrement to go down from 2,700 to 1,000. The formula we'll be using is A equals B into 1 minus R to the power of T instead of plus, because this is a decrement. Then A would be replaced, the final is 1,000. Now the original was 2,700. Okay, so 1 minus 0.05 to the power of T. So we are dividing by 2,700 by 2,700. So this is gone. When I divide 1,000 by 2,700, I did it in the calculator, it would be 0.37, approximately that. Okay, and then this equals 0.95 to the power of T. So I'm changing this to logarithm. I change this to logarithm, which is log base 0.95 of 0.37 equals T. This gives me the time. So last week, you remember we did this mean log of 0.37 over log of 0.95. If I do this using my calculator, I find approximately 19 years. In 19 years, probably if this was in 2000, the average cost of the computer in 2019, probably it came down to 1,000 on average. Okay, this is one example we have for decrement. For decrement, applying logarithm to find the number of years for a price or cost to go from 2,700 to 1,000. Okay, let's see example 3. This problem has been done with estimation or with using table last week or before last week, I think. Since 2000, college tuition rates have increased by about 5.3% per year. If college tuition originally cost 20,000, how long will it take for it to double? Okay, now we are going to calculate still how long it takes with that percentage to go to 40,000, say from 20,000. Let's put the problem. Example 3. Solution. Okay, the original amount P was 20,000. the final amount we are looking for is 40,000 because it's doubling. Okay, the interest rate is 5.3%. So this means 0.053. We go to the left 2 decimal points to the left, 0.053. This is increment. Since this decrement, this minus becomes positive. A equals P into 1 plus R to the power of T. Okay, the procedure is really, it is repetition. 40,000. Here you have 20,000. 1 plus 0.053 to the power of T. So the same thing we do. The procedure is the same. You divide by 20,000 first, so that you get 2 here. This would be 2 equals 1.053 to the power of T. So what we are changing is we are changing this to logarithm. So T would be log base 1.053 of 2, and then I'm approximating this, dividing log of 2 by log of 1.05. That is how it works. Okay, so if I put log here, log of 2 divided by log 1.05, that is change of base, change of base property we have seen last week. This will give me 14 years, approximately 14 years. 14.2 says I can take it approximately 14 years is what it takes. Okay, let's take the last example. The last example for our modeling by use of logarithms. This is our last example for let's say a group of 10 leopards is introduced into a game park after 2 years. The number of leopards now n, suppose if you call the number of leopards n, is modeled by continuous growth. If the rate of growth is 40%, write the equation used to determine the number of leopards in t years. Determine the number of years needed to see 100 leopards in the park. See, okay, so now they were first 10. The growth rate is 40. It is continuous growth. So how are we applying, or are we solving this? Example 4. Solution again. Okay, so first they were only 10 in the park, and then we want to see to write the equation first for the final to be 100 with a rate of 40%. 40% is 40 over 100, or if you want to translate 40 over 100, which is 0.4. 0.4. So the first one is asking you the formula. It is continuous growth. Continuous growth. The formula we are using is A equals P e to the power of RT. We are not using the one which says A equals P into 1 plus R to the power of T. This is used only when it is compounded annually, something like that. Okay, so we are using this. A is 100. It started with 10. This formula equation is this for question A. Question B, how long it takes to go from 10 to 100. E 0.4t. This will be the equation we have. we're going to solve just this, converting it to natural logarithm. But first, if you take logarithms or just divide by 10, it's gone. So 10 equals e to the power of 0.40. First, not to be confused, just change it to logarithm, which means 0.40 would be log base e of 10. But I know log base e means ln, or natural logarithm. I'll replace that. 0.40 equals ln of 10. The ln function is just below the logarithm function here. It's just below the logarithm function. So I press ln of 4 is 1.386. So let's take 1.39. So 0.40 is approximately 1.39. So once I get that, what I do is I divide by 0.4 to get the time it took from they were 10 in the park. Lately they changed it to 100. So to get that, divide this by 0.4. Okay, so this gives me the time it takes, approximate time it needed. Divide 1.39 by 0.4, you get 3.475 years. 3.475 years. Okay. You can call this 3 years or 3.475 in months, in days, you can calculate it. Anyway, this is all about modeling with logarithm, including the natural logarithm. That is for today. Yeah, I hope this helps you a lot to do your next assignment or week 5 assignment. Thank you.